So if there's no questions, then we're going to start the next section and we'll wrap this up today. It's pretty simple section. Sure, if you want, but you could always have email. Well, maybe if it's a quick question, then go ahead. Yeah. In the project goals. So people can't see this. He's asking a question about the project. All right. Right. So you have to create a schema and then you have to provide me. So he's asking in a project goals to deliver an SQL script that will create a simple customer schema on the instructor's PC for grading purposes. What is the scope of System Customer? The simple customer is the schema that implements the schema that you need for the for the application. Does that answer your question? All the create tables. Okay, kind of, he says. And I'm waiting for him to finish typing something, I think. Yeah. Does it follow the description of the entity classes? Yes, it does. That's the whole point. Yes. The customer schema as provided in the documentation. Okay, you done? Is that good? I guess okay, I see now means is good. Okay, it's good. All right, moving on. Um, okay, so we're going to do section 7, and it's about entity relationship modeling. So this section is concerned with the process for developing the a schema, typically for a brand new application. You're starting from a new application, you have a new project, and you're developing the schema for this new project. Well, this schema, the database design, doesn't happen in a vacuum. It happens in the scope of the larger software development project. So that brings us to more of a software engineering topic. But if you've taken software engineering or maybe the computer science 2 course, you'll know something about the project lifecycle. And so a project lifecycle is simply a name given to the activity of the team activity, the group activity of building a software system, of building and delivering a software system. And so usually, not always, unless it's just some kind of standalone hobby project or something, a software development system is delivered in the scope of some kind of project. And a project has a defined date range. So we have a start of a project. It begins, and I'm just going to use something simple, on January 1st, just because it's something simple. And it has a duration. How many days, months, weeks, weeks, months, maybe even a year is needed by the development team to implement and deliver a working system. And so that range defines the end. So we have the start of the software development project, and we have the end, the estimated end anyway, and we're going to say this is going to take 10 months, so it'll be delivered on what will it be? September, October, November, October, or November 1st. Okay, so 10 months. All right, so that's a nice start. So this is the life cycle. I'm going to regret having written that in a second. Okay, so that's not enough though. This is, actually, how does that work? Well, the team starts on the first and they do some stuff and they write some code and they do a little testing and then somebody signs off on it and at the end they deliver our software. But that's really not, good enough. So what they have, what we have in software engineering, and many variations on this theme, is we divide that life cycle into a we partition that time, that life cycle, into a number of activities that are executed by the software development team during that life cycle, or in this case, during those 10 months. So we're saying that, according to the process that the team is following, they're going to first execute a requirements phase. And once they finish gathering understanding of the requirements, they enter an analysis phase where we'll talk about this coming up. And after the analysis is completed, they enter a design phase where they actually design the software. And then there's a construction phase where they have a really good, based on these previous activities, the development team has gained a sufficient understanding of the problem domain and the data structures and the algorithms that will, solve the problems in that domain, and will build a system that the customer needs to will find functional, will find useful. And so they start the process of implementation, of building the system. And then at the end, in most cases, before a software system can be delivered to the customer or can be put into production, made accessible by the public, it has to go through some sort of final testing, integration testing, which is supposed to identify all of the bugs that the developers missed. And once that's done, then it's, party time. It's Miller time. The system should be delivered. Okay, so these are phases, and if we looked again at our little slide, this idea, if we say that this is 12 months, then they're going to spend, 3 to 4 weeks, or maybe 3 weeks doing requirements, and then some time doing analysis, and then design work, and then implementation always takes up the bulk of it, or should, and then, integration testing needs a fair amount of time, because again, this is where the QA, quality assurance people, will identify all the bugs that the developers missed, and they can get quite lengthy in terms of fixing or integrating new features that they missed. Hopefully not too much. I mean, that's the whole point of requirements analysis design, is to keep the development team from implementing an incorrect or a system that lacks features, lacks needed functionality, or is somehow flawed. So the better job the team does with requirements analysis and design, the more likely the system that they deliver to integration testing will be complete and will have a minimum amount of rework required to get it ready for delivery or to be put into production. Okay, so this is software development. But again, like I said a moment ago, part of software development is the database design and implementation development. So okay, and so this is all the database. A little bit of database comes into each of these phases, each of these activities performed during the development or integration is devoted to developing the database, developing the DAOs, developing the services, all of the functionality or the classes or services in the data tier. 3-tier architecture has presentation, service, and data tier. So the data tier, of course, is where the database comes in. So developing the schema, coming up with testing, coming up with scripts to populate the tables for testing. Just a lot. There's a lot to do. Okay. So that's the generic software development lifecycle, and again, part of this process is the is the development of the database. One more thing about this this diagram, it indicates that the beginning, then again, like I say, first requirement activities are executed, and during or a product of the requirements activity is to produce some artifact, some information. And so, for example, and again, just as part of the software engineering curriculum, when the team is executing requirements during that 3 weeks or a month or whatever, they should be putting together a document that lists a set of formal requirements. And that set of formal requirements should describe each and every feature that the system will deliver for the customer. And it needs to be complete and exhaustive, which makes it a little bit difficult to put together. And one of the purposes of this document is to present to the customer, who then reviews, or is supposed to review these requirements and signs off on them, saying that yes, this list of features and services and entities and so on that you've identified, meets our, well, not so much the entities, but the set of services that you've identified to be built during these later phases is in fact, meets our needs, the customer's needs, and you can move on. So one of the things about requirements is it kind of builds a contract between the customer and the development team. And the development team lists what they need to do, what needs to be done, what needs to be delivered, and the customer signs off on that, says, yes, this list is complete. And now the team, in theory, the team has everything they need to successfully execute the project, and again, at the end of the day, deliver an executable system. At the end of analysis, when the analysis phase is completed, they'll produce business and domain models, which might include the ER diagrams, which should include the ER diagrams. And then at the end of the software design, implement perhaps the, well, we'll talk about this coming up. But at the end of each phase, a certain artifacts are delivered for the, for the database development effort. And we'll talk about that in the coming couple slides. Okay. Well, the book has, just like this is the generic software development lifecycle, the book has their own lifecycle. And that's what this is showing here. So just like I was showing more or less horizontally, this produces that, and then this is input to that. So I guess implied here is the requirements form the input that the team executes the analysis activities against, and that the domain models, are the input to the development team's efforts in designing the software, and so on. So this produces that, and then this information is the input to these activities, which produce this information, which is the input to the next, and so on. Same thing's true here. So I've kind of stole this from the book, and this is the 4 phases that the author talks about in the book. And then next to each phase, I've placed the SDLC, the generic SDLC phase that corresponds to the author's phase. So his process has these 4 phases in it, and then each of those phases produces these this information, these artifacts, these things, and we're going to talk about each of these in turn. But you could see that, and I'm sure it's no mistake, that these 4 phases correspond very nicely to the generic software development lifecycle. So conceptual, logical, and physical. All right, so requirements collection. Firstly, requirements phase. Collect system requirements from the problem domain, subject matter expert. So again, I don't want to spend too much time on software development here, but most of the time, if not every time, the development team, lacks knowledge of what it is they're, supposed to implement. If the software development team knew exactly what the customer wanted, well, they're probably the customer and they're writing the system for themselves. But most of the time, the developers are working for an internal organization like a development team inside of State Farm, or they're working as a contractor, like Raytheon is working as a consultant or contractor for um, the Navy or one of the defense departments. And so the in both cases, the customer, whether it's an internal customer from within the sales department within State Farm or the Navy coming to Raytheon, the customer has something they wish to accomplish. They say, we need this system to accomplish, to solve this problem or to implement this service, which incidentally is going to make us money. And we, the marketing department, lack the software development skills, computer skills, to make that happen. So we are going to hire you, the development team, to implement this system. And the development team should say, what system? And then the customer will present, hopefully, a number of individuals who understand both the problem domain, insurance processing, or communication systems, or whatever it happens to be, and also understands the problem to be solved. So these subject matter experts, are needed or communicate with the development team, and the development team will interview and extract from the SME everything they need to know to build the requirements. Um, Now, sometimes, just as a matter of interest, within the development team, the developers don't, the people writing the code don't actually interview the SME. And organizations, large organizations, or even medium-sized organizations, they hire individuals called business analysts or BAs. So the business analyst is kind of the go-between between the subject matter experts and the development team. So a business analyst is a person who's really good at communicating with uh, people, so to speak, as a people person, and can elicit the requirements and can record those requirements in documents, requirement documents, and then those requirement documents will be handed off to the development team when when the time is right. So there's always, this is kind of a nice thing, my experience, to have a business analyst who is good at building requirements. It's kind of a tedious thing to do anyway, and business analyst again is trained in how to interview and extract information from others, and so they work out pretty good. It's a nice practice if your company is exercising it. Anyway, so at the end of that process, the business analyst or the development team themselves, if that's who is interviewing the subject matter expert, will put together will have a set of requirements. So those requirements can be recorded in several fashions, but we're not going to go into those details in the database course. But two of the primary ways of gathering requirements is through functional requirements or use cases. In case of use cases, that includes like stories from Scrum, um, and other ways of capturing um, sort of capturing in a non-formal method, the systems requirements. Anyway, again, that's not something we're going to talk about anymore here. I just thought I'd mention it. For functional requirements, though, functional requirements are declarative statements. So, as an example, and I was thinking about this 10 minutes ago, so let me see if I can do it again. For e-commerce, a requirement might be the system shall provide individual users a home page which contains product descriptions for products that the user or the customer has previously shown interest in, whatever that means, and they would define that in more detail. Another requirement might be the system shall allow unregistered users to register with the system. Um, this is the registration process shall provide the user an account and password. The system shall record the customer's first and last name, date of birth, gender and whatever other address and credit card information. The system shall, and so painstakingly, in painstaking detail, um, there are dozens, hundreds, thousands of individual statements recorded that describe, what the system should accomplish. And these, once you get into the thousands, these statements, these documents are divided into sections. One section for order fulfillment, another section for order for product management, another section for customer management. So to make it a little bit easier. But a lot of requirements for even a medium-sized system. Okay, so enough about that. So those are, but anyway, at the end of the day, these requirements are gathered and recorded and into a document. And then again, like I said, the customer is usually required to sign off on those requirements before the team transitions from requirements into the analysis. Or in this case, before they transition from requirements collection into conceptual design. Now, another thing I want to mention about requirements is this idea of non-functional requirements. So non-functional requirements usually specify constraints on some non-functional aspect of the system. And the one that comes to mind most, for me anyway, is the idea of performance. How do we can build a system that meets all of the functional requirements, but is extremely slow. And so the customer can't use it. If the system can only support, let's say, 1,000 transactions per minute, but the customer expects to see 5,000 transactions per minute normally, well, then that system is useless and should not be considered complete. And certainly the customer won't want to pay for, that system. And so, but it has to be recorded somewhere in the system's requirements has to be recorded these types of constraints, these types of requirements. The system shall maintain 5,000 transactions per minute for 24, across a 24-hour period, some sort of statistic, some way of specifying, or maybe uptime is another good example. The system shall remain available for 365 days a year and shall suffer no outages greater than 3 hours, something like that. I don't know. But anyway, these are all non-functional. They don't really describe individual requirements or features that need to be accomplished. They said they usually define requirements that span the entire system. Performance is, we're not saying performance, encompasses all of the system's capabilities, availability, reliability, all encompass security. Nowadays, security is a big thing, recording the security constraints or requirements. So all of these things, these non-functional aspects of the system are recorded and as non-functional. And of course, that kind of, performance is a big one. Databases are usually the bottleneck in the system, usually a central point, a bottleneck, so to speak. And so in terms of how to deliver the performance that is needed, we need to optimize the database performance by adding indexes or materialized views or other forms of caching. But, it has to be understood right up front, what the system should deliver. And again, and the database has to be designed around that. All right, so that's requirements, both functional and non-functional. And again, that leads us to the next phase. And so in database terms, the author's process is conceptual design, and I would say that this is the analysis. Now we're going to talk more about analysis and see how far we get into the section. I want to finish it today. But during this second phase, the analysis or the conceptual design phase, we're going to identify the entities. Now, this is very specific to the database, and there's more to it in the general software development terms, but from a database perspective, during the conceptual design phase, the team, and now this is usually the development, not the BA, is going to identify all of the entities the entity classes from the problem domain. So, now from a database perspective, we're most interested in those entities whose state must be persisted. So, and most of the time, every entity class we identify, is to be persisted. So what are entity classes from ecom? Well, we've talked about them a lot. We have customer and credit card. In fact, you're working with one right now, right? We have customer, credit card, purchases, product descriptions, orders, just countless others. So each of those, from a software engineering perspective, is a class, right? We're going to have a customer class and just like, from the project, and an address class. And there's an association between customer and many addresses and so on. Excuse me. But we also could identify some entities in our software design that won't be stored in the database, that won't be persisted. So as an example you might say, well, and this would have to be spelled out in the requirements. A customer has a shopping cart. They log in and they make selections, and those selections are placed into this shopping cart, which is just a list of selected items. But we give it a name because it might have other properties. And but do we persist that? And so that's a larger question is, does a customer's selections persist across multiple sessions with the system? If I logged in yesterday and browsed, spent 10, 20 minutes browsing some material for some products and placed them in my shopping cart, but I didn't purchase them actually, didn't order them, and I leave, get interrupted for some reason, and I come back today, will yesterday's purchase selection still be in my shopping cart? Well, if the answer is yes, then that means we will need to, every time the customer updates their shopping cart, we'll need to persist that information on the database so we can retrieve it later. Amazon, of course, does this. If it's a no, then we don't have to. And maybe you should tell the customer, well, we don't need to persist. If we persist shopping cart, it's going to add a week to the schedule. What's the trade-off? They say, well, why wouldn't they just say yes? Why not? Well, you can make, it's one of the parts of negotiation to some extent. No, I don't know if it gets this detailed, but what you can say, if it is, you can give the customer the choice. If we are going to persist your shopping cart, it's going to require 40 man hours to implement, or 45, whatever we're estimating, and that will have to be accounted for in the schedule and in the budget. And so it'll push your project delivery back a week, and we'll add an additional, $70K to the cost. And the customer can say, well, maybe I don't need that shopping cart persistence after all, and drop it. Or, say, push through and say, yeah, it's worth it. Let's do it. Okay, so that's what we're doing. We're identifying, during analysis, during conceptual design, we're identifying the customers, the entities, the entities in the problem domain, and we're identifying their attributes. We're saying that a customer class, we're going to persist the customer's first, last name, and date of birth, specifically not address or credit card, date of birth, and I don't know what else, depends. That's what we're coming up with. And then, those are recorded as classes. And then again, as we talked about this idea of object relational mapping, the class becomes a table, and the attributes of that class become attributes of the table that represents that class. So each attribute in the problem domain that to be persisted, is a attribute in the table, and that's part of the database design, part of the schema, and so it needs to be captured, and scripts have to be built, and so on. Also, of course, the data type. Is it float, a string, whatever? Can it be nullable? Is it an optional thing? Can we allow the customer not to provide a date of birth, and which would make it a nullable attribute? Or are we going to require that? It just depends on the requirements. Other constraints. And then also we're going to identify relationships between entities. So just from your ecom example, we have a customer class, and then we have multiple credit cards and addresses. And so we'll identify those relationships between entity classes as being one-to-one or one-to-many or many-to-many, or maybe there's no association. I should put that down here. No association. They just aren't associated. The vast majority of classes aren't associated. Um, so that would work too. Finish. There we go. All right. So back still here, the entities are recorded in one or more diagrams. So, we capture software designs in diagrams, and we capture software designs in UML. I mean, that's the way to do it. There's no other way. That's the tool. And it's always a good idea. And to be good, if you want to, be a proficient software engineer, you really should get used to using a UML editing tool, a real UML editing tool, not Glyphy from web, and then get good at capturing a design in UML. Enough said. And then, of course, for a database design, you need to capture those entities which are going to be persisted as entities in a entity relationship diagram, which we've been working with, which you worked with on MySQL Workbench. Now, and there's an alternative. You can just write the create statements without going through the entity relation modeling tool. You can you can build the create statements by hand. It's just a script after all in the end. But anyway, in this course, we're going to build the ER diagrams as well. Okay, so that captures the data, but there's still more. But wait, there's more. We have to consider the operations that will be performed on the persisted entities. And these will come from, again, from our functional requirements. As an example, if this is econ, we might have a report where we wish to present to the customer all of the purchases they've made, within some beginning and end date range. So, that information is in the database, and it might be required to join, the purchases table with the customer table, and join a couple of tables together to extract the information. And so, we have to, in order to support that report, we have to know that the schema, the associations in the table, in the associations between the tables in the schema, will support the query needed to extract whatever report. And of course, that's a very simple report. There could be far more complicated reports you need. Or update operations or whatever. So there's operations to be provided, services to be provided by the system to the user, to the customer in this case, that will require support from the database. And so during this analysis phase, we should identify those operations and ensure that the database schema will support the associations needed, foreign key associations needed to produce the report. And then we need to design our DAOs and data tier services to provide endpoints that our clients can use to request and receive the data in those reports, and so on. So it's not just the entity classes and their associations and their attributes, but also the data operations that will be needed, the system needs. Reporting is a good example, that the schema needs to support, and that the data tier services, DAOs, and data tier services and DAOs also provide interfaces, to access those, to query, access those services needed to produce the report. All right, logical design, next phase. And this shows the design phase in the SDLC. Convert the entities, attributes, and relationships into a schema for a particular design. So this is, this is a little bit, where's the difference between conceptual, analysis, and logical. And just like in software development, it's kind of gray. You know, where does the analysis activities leave off and the design activities pick up? They're very clearly defined in the generic software development lifecycle. However, you know, it's kind of a it's kind of an artificial partitioning between analysis and design, you know, there to make clear that these two activities exist. But many times in practice, the development team will execute, you know, both at the same time. I don't want to get too deep into this, but it kind of depends whether or not how important analysis is separated from design depends on how well the development team understands the problem domain. If the if the development team has never built I'm going to stick with ecom, why not? Has never ever built an ecom site before, as maybe, you know, let's imagine we're going way back in time till the late 80s, early 90s, and, you know, there's, you know, these idea of ecom, Amazon is brand new, you know, so it's kind of a new idea, purchasing stuff online, browsing for and making purchases online. And so nobody has a lot of experience with this. Or maybe for a military contract, they're building some sort of robot, I don't know, whatever. If the team has no real experience with the problem domain, then the amount of effort they put into analysis before design, it becomes very important. You know, once it starts designing, developers are kind of one track. They start thinking of algorithms and data structures and coding, and they won't see the missing details. You know, they'll be focused on the solution, and, you know, and not what the solution is, or at least the solution as they see it. So the more time, if a team is not familiar with the problem domain, they really should spend a fair amount of time in analysis just identifying entities and services, and in order to make sure that they've completely modeled, correctly modeled the problem domain to meet all of the system's requirements before transitioning into design, where they start, you know, the fun stuff of designing algorithms and data structures and schemas and coding and so on and so forth. You know, developers want to get to that, and if they haven't a sufficient understanding of the problem domain, they're going to build a system that's missing features, and then those that will those missing features will be discovered during integration testing, and then, you know, they wind up tacking another 6 months to the project to accommodate all of those missing features that they should have caught during an exhaustive analysis, and that's bad, obviously. Okay, but just conversely, very briefly, if the team is built, you know, say it's today, we've built, you know, a dozen or so ecom sites, and this one is pretty much the one I'm building now is pretty much the same as the last dozen, but, you know, there are some subtle differences in how orders to be processed or how information is presented or whatever the differences are, and we need to capture that. But for the most part, you know, this system is going to be 90% of the last 5 systems I've built, and analysis is not that important. Anyway, during design, the team will, you know, they're supposed to develop the schema. And so while during analysis, during the conceptual design, they may have put together, let me close my box here. They may have a detail, they might have an ER diagram. Well, now they have to think about how the system is actually going to be built. You know, how the tables, we have to put together I'm putting in this slide. They have to create the schemas, which, you know, may not be a big thing if you're using a tool like Workbench. But anyway, that's what's going on here. Like I said here, if the conceptual design was captured in an ER tool like Workbench, then design is not really all that, doesn't require that much effort. Then the physical implementation. So just like implementation in the generic software development lifecycle means building the system, coding it up, so to speak. In this example here, we're talking about, you know, refining the database design. So again, because we are supposed to have developed the schema during the logical design phase. At this point, we're just basically looking to optimize the database, usually to meet non-functional requirements. We said before, non-functional requirements usually revolve around performance, availability, but also these days increasingly security and other usability, perhaps, how easy is the system to learn. But at any rate, in terms of implementation of the physical design, the the database designers will start considering how to modify the design schema to meet the performance requirements of the system. And this might include benchmarking and stress testing and stuff we're not going to go into here. But how to do caching, how to build materialized views, and maybe put caching in at the service tier. There's a lot of optimization for caching, and again, we're not going to talk about that here. One thing you can do is if a query is running slow, you can every database provides, every vendor provides a facility that allows the developer to understand how the system will execute a given SQL query. Now, this is usually most useful for selects because selects always require the most bandwidth. Inserts, updates, and deletes are usually very straightforward, but the select, is where you start joining tables together and doing correlated queries and so on, and that's why they're slow. So if you have a query and it's a select and it's pretty slow, you can use the explain facility offered by the database. All the database offer this, and I was thinking of going into this last time in the last section. I forgot to, but you could do this. Take a query, a select statement, take one of them from from the slides in the last section, and then so you'll have a select query, select from blah blah blah. Just put explain in front of it. Just type the letter the word explain in front of the select, and then run that query, and you won't get the result set. Instead, you'll get the query plan. You'll get exactly what steps the database is going to take, what tables it's going to look into, how it's going to look for them, and so on. And usually you're interested in looking for table scans. Anytime the database is going to scan the entire table for a given attribute value, and at that point, you're usually going to add an index. So if you run a query, the query is running too slow, and you ask the database to explain what they're doing, what it's doing, and it'll tell you, and you'll look for table scans, and you'll say, oh, this attribute's got a table scan, and this is a very large table of 100,000 rows. That's one reason why it's slow. And so then you can add an index to that attribute, and it'll speed up it'll remove the table scan and probably speed up the query quite a lot. All right, so explain, check it out. It's good to know. Okay, so that's it. I mean, that's our 4 phases as far as we're going to go with the 4 phases of this process, development process that is suggested or described by the author in our text. Any questions about that? Okay, so let's talk a little bit about ER diagrams. Now, we've covered this before, and you've been working with ER diagrams, so there's really not that much to talk about, but the book, that's one of the keys of the book, of the chapter, so we're going to spend a little time talking about it here. Now, there's actually one of the weird things about ER diagrams is there's so many different types of them. Yeah, there's you can look at this link here, but there's lots of them. And one of the reasons for that is that there's been no effort to standardize the notation. Contrasted that with UML, Universal Modeling Language, or I'm sorry, I always do that, Unified Modeling Language. Prior to UML, back in the 90s, there were like dozens of ways of drawing class diagrams. There were, an author would make a book by, coming up with a process. Object-oriented was relatively new, and so everyone wanted to climb onto the the object-oriented bandwagon. And so there are a lot of authors that put together, that made a few, and this is back when books were still, something you purchased and put up on a shelf. So, publishing a book, and in their book they usually had their own notation. You and so there were a lot to choose from, but it was a problem because there were so many to choose from, and and the support drawing tools like UML editing tools you have nowadays, were expensive and pretty buggy too. But after the UML people, there was a push in the industry, probably top down from the customers, to standardize the object-oriented process to the extent possible, which gave us the unified process, UP. And then accompanying UP, unified process, was the unified modeling language, UML. And while UP is seen some success, UML is hugely successful. And so that's why we only have one. That's why we have only one UML and many different ER diagram notations. Okay, anyway, enough of that. Here is an example of the company schema that you all come to know and love. And this is for, this is called Chen notation. And my God, what an ugly, ugly mess, really. These are entities, tables, these are attributes, but no data types. And these are associations. The triangles are associations between. It looks a lot like a flow diagrams, flow charts, I should say, from back in the 80s. I guess that's it's where it came from. But anyway, that's the one the book kind of uses this a lot, and it's so bad. Anyway, here's Crowsfoot. In my experience, Crowsfoot is where it's at. Crowsfoot is what most people are using, most companies, most individuals are using Crowsfoot notation, and so this is the one to become familiar with, but you should be already. Just very briefly, Crowsfoot notation divides these rectangles. Each rectangle represents a table, and each rectangle is divided into 3 sections. You can figure this out as well. The table name, and then these 2 sections containing attributes. The upper section, divided, with this line. The second section, this section is contains all of the table's keys, and so we have employee, and we have the super SSN, which is actually a key back to itself, and then department number is a foreign key into the department table, and then a primary key, which in this case was Social Security number, SSN. So how do we know it's the primary key? Because it doesn't have an FK on it. Now, why they didn't go the extra mile here and add PK to to specify, make explicit that this is the primary key is beyond me, but that's that's how it works. So any key without FK is the primary key of the table. And now and then every attribute in the lower section is a non-key attribute. And of course, we're including the data types and all the good stuff. And it's very complete and very helpful notation. Also, of course, we have these associations. These, just like UML shows associations between classes using associations, we're using these Crowsfoot associations. And we've seen, here's another same diagram, same information, except a little bit different format. So this is an ER diagram generated by a tool called ASTAH, A-S-T-A-H, and it has ER modeling capabilities, and so we are showing that. A little bit different, in fact. This is a different problem domain. This is the company, and this is, oh wow, really? No. Sorry, I just want to. There we go. The different problem domain. This is like a game schema capturing the player, their games they played, and some other stuff. So there's another project. You did the econ project. There's another project that uses this schema. But anyway, all right, crow's foot notation, where this is showing an association between two entities. And so we have uh, at each end, we have a symbol that denotes, one side of a two-way association. So we have one-to-one, one-to-many, many-to-one, and so on. Each end, this would indicate at this end, this symbol indicates that this side of the association, we have 0 or more. And so this would be the same as an asterisk in UML. So we can have 0 or more associations. Here is 1 or more, so there must be at least one instance of an entity associated with this side. So like if this was customer on the one side and credit card on this side, the business rule says that every customer must be associated with at least one, maybe several credit cards, or one, maybe several addresses. Well, you would use, if the requirements call that out, you would use this symbol. If the requirement said that, for whatever reason, a customer can be associated with 0 or more credit cards. Maybe you don't want to ask them to add it immediately. But anyway, that would be the symbol. And then just like from UML, we're saying that the 2 lines, that means that there's only one and only one. So if we were somehow going to restrict the customer to a single credit card, whatever reason, that would be the symbol. And then 0 or 1, this is either 0 associations or at most 1. So 0 or at most 1. So, and we can combine those together. This is entity 1, entity 2, and so on. And it's pretty straightforward. Are there any questions about it? So crow's foot notation. Okay. All right, let's talk a little bit more about entities. So an entity is something in the real world with an independent existence. So, we often identify entity classes in our software engineering process. Now, we're not going to get into it. Well, I'm sorry, I am going to get into it. We'll see how far we get in this section. But, we identify something in the real world within the problem domain, but in the real world with an independent existence. And so, a customer, as we're modeling in an ecom, we're modeling a customer. And for every instance of a customer, there is a real world person out there who has registered with the site, providing their information, has been assigned a unique ID, and then recorded, in one or more tables by the system, the customer table. And again, a customer, there's purchases, are real, there's a thing, a product that can be sold, that is being sold, and will be shipped to the customer. Purchases and then orders, what purchases has the customer made, at a particular on a particular day. It's a purchase. And while there's not a thing, not a physical, unlike a customer or a product, a purchase isn't a tangible thing that we can touch. It doesn't have a physical presence. It is an individual instance of something in the problem domain that we wish to capture. It's an abstract idea, but this customer purchased these things on this particular day, and those things were shipped at this particular day and time, and we need to capture that information about who purchased what and for how much and when they were delivered and so on. We have to capture that in some context, and so we call it a purchase. So it's an entity, and the system maintains entities. The system will CRUD entities, not really shown here. I should put that down here. Systems generally are written to CRUD entities or parts of systems. We'll have a customer service subsystem on our ecom site whose purpose is to CRUD customers. And we'll have a product management subsystem within our ecom to CRUD products, and so on and so forth. And so object-oriented systems have instances of entities, which are maintained in memory. And relational database have tables, and for the classes and rows that represent the individual instances of those entities. Now, there's 2 types of entities that we'll talk about: strong and weak entities. We really haven't talked too much about weak entities, but we have talked a lot about strong entities. Essentially everything we talk about so far we've described as just an entity, a table, which we haven't really differentiated between strong and weak. So a strong entity is an entity with an independent existence. So customer is a strong entity. Strong entities have primary keys that uniquely identify each instance of that entity. So every customer has their own ID, every product has a unique ID, and we can glue those together using foreign keys and so on. So, okay, what's a weak entity then? Well, a weak entity isn't really treated any more differently in the schema or by the database than a strong entity, but it's something we differentiate in the design we think about because it helps us, build better systems. So a weak entity is just an entity whose existence, there's different ways of describing it, but the simplest way is an entity whose existence depends on an owning strong entity. So one of the things about a weak entity is that um, every instance of a weak entity must be associated with a strong entity. Okay, so from examples from our ecom, address and credit card can be considered a weak entity owned by the customer entity. So why? Because if we delete a customer, well, we're going to remove their credit cards. We have to remove their credit cards and addresses. There's no point. In fact, it would be an error to maintain a credit card or an address when there's no customer, corresponding customer in the system. And that has to do with the foreign key dependencies and foreign key constraints. We can't delete a customer if there is an address or credit card in the system. From the company schema, we can't delete an employee if they still have a dependent in the system. In that case, the employee is a strong entity and the dependent is the weak entity. And in fact, if you look at the schema for weak entity, it doesn't have a primary key. So it's actually a very good example. And so on. So that's the point. A weak entity is an entity whose existence depends on, is associated, whose dependence depends on an instance of a owning strong entity. So, kind of saying it again, weak entities has an existence dependency on a strong entity. A weak entity can't exist independently of a strong. A weak entity is not, so here's one indication of what's a weak entity. A weak entity is not queried independently of its strong entity. So, if the requirements have no need to retrieve a address independently of the customer, well, that's a very good indication that address is a weak entity. If every time we access a address, it's through its owning customer, then we're not independently querying address table, and so we don't necessarily, that makes address a weak entity. Same thing for the credit card. Weak entities don't need a primary key, but if you want to add one to the table, there's no harm done. It's just a little bit of data. Just wouldn't worry about it. It's nothing to sweat. But like I said, the dependent table from the company schema, does not have a primary key, or if it does, it's the employee social security number and the first name. But at any rate, it doesn't have a surrogate key. And of course, every weak entity must have a foreign key back to its owning entity. So credit card and address table must have a foreign key back to the customer table. And it has, this is well established. The Chen notation has its own way of representing weak entities, and so does the crow's foot notation. So these things, these differences between weak and strong entities can be shown graphically, diagrammically, if that's a word, in our ER diagrams, and it's up to you to kind of figure out how that works. In fact, to some extent, sometimes it's different from one ER diagramming tool to another. Workbench might do it differently, show weak entities differently than, let's say, the ASTA modeling tool I showed a moment ago. So to some extent, you have to figure it out. for your given tool, how to denote or show a weak entity. But anyway, let's not get too deep into that. Okay, so that's the difference between weak and strong entities. It's mostly the stuff on this table, and mostly the idea that we are not querying a weak entity independent of its strong entity. We don't query, have requirements to query for addresses independently of the customer that owns them, and so we make address a weak entity, and so on. All right, so moving. Is there any questions about that, or we're gonna move on to something else? Okay, so let's talk about two different types of attributes: simple and composite. One is good and one is bad. Simple attributes, again, remember an attribute in the table is a column. It's a property of the entity that we're capturing as an attribute. And a simple attribute describes a single thing about an entity. And so you might say, well, that makes sense. Um, so in our company schema, we had first name, last name, middle initial. So each of those is a simple entity because it describes a single piece of information about the employee. We can't break down first name into anything else. I mean, we can break it down to its letters, but that doesn't make sense. You know, a composite attribute describes in a single attribute several things about the entity. So a composite attribute can be divided into subparts, and each subpart has some independent meaning in describing the entity. So, for example, if we had an employee schema that had a single name attribute, but we wanted to capture the first, last, and middle initial of each customer, then we might build a compositive attribute called name, and each name, the value of each name in a row would be a string, and the separate components of that name would be separated by commas. Now, this is just one way of implementing it. There's nothing in SQL that says that, you delimit using a comma. I'm just using it as an example. It could be a semicolon, could be a space, so that might get you in trouble. Could be an asterisk, could be any symbol, any character you choose. The problem is once you choose that character, you can't use someone's name. So if they're, anyway. Okay, so here we have a composite attribute, first name, last name, comma, middle initial. Okay, and that would work. I mean, it's not a good idea. We'll talk about why, but that's a composite attribute. Address. This is even a more blatant example. Let's say instead of having a separate table for employee's address, we have a single attribute, a composite string, a varchar 50, and in that single string, we encode all of the information about a customer. So let's say we're going to put another comma there. Let's say suite 100. Thought I'd make it a little more complicated. So in this composite address attribute, single attribute, we've encoded the street address, the optional second street address. So if there was nothing, we just have a comma, space comma or something. But here we're going to have apartment numbers, box office, for a post office box number, suite number for business, comma, the city name, comma, the 2-digit state code, comma, in this case, we're just going to use the 5-digit zip code. So 1, 2, 3, 4, 5 pieces of information encoded into a single attribute delimited by commas. And that's a composite attribute. So we want to get rid of them. There's problems with it. For example, we can't query. Now, the like capabilities, how do you query for wildcards in SQL? In theory, bring back this. Let's get rid of this. Oh, it didn't work. Hmm. Oh, I know I'm doing wrong. There we go. Okay, where was I going? If we wanted to, let's say we have Smith, comma John, comma C, and that's a string, and that's the name attribute. Well, how do we query for everyone, with the first name? Okay, let me change this up because I should have put uh, first name first. Then my example would work. So John, comma Smith, comma M, using an example of the slides. But maybe I want to query for last name. Well, how can I do that? How can I write a query where I want to identify all of the employees whose last name is Smith? Well, you could use like to some extent. You could say select from employee where name like, and then you could say I think star comma Smith, and then comma star. I think I'm doing that right. Honestly, I don't remember. The wild card and likes, I believe, is an asterisk, but am I just thinking it because that's what it is in regular expressions? Let's go with it. Anyway, okay, I'm tempted to interrupt what I'm doing and make sure I'm getting it right. Does anyone remember? I'm I'm not proud. The wild card and like statements. I don't want to go and look online. Well, anyway, I'm going to stick with that. So that's kind of, that's troublesome. What if they have a space in their name right there, and then this wild card would match? Um, no, I don't know. It's just difficult to identify using wildcard, reliably write queries using the like statement, wildcard capabilities to identify particular people with particular attributes. Maybe you want to identify everyone whose name starts with SMI. So you go SMI star, comma, star. I don't even know if that would work. Um, it's just very difficult to to query a complex attribute. Uh, Worse yet is an address. So you can say where, maybe you want to know everyone in Chicago or everyone, yeah, in the city of Chicago. Well, we have to do where address, which is the complex attribute, composite attribute, like, I think it's question mark now. I'm sure it is, in fact, question mark. That's correct. Um, like, now we want Chicago, right? So we want to do something like First Street, question mark, comma, delimiter, second part of the address, question mark, Chicago, comma, and then question mark for the text, question mark, and I don't even know if this would work. Okay, so now that would hopefully get us to the 1, 2, third element of our composite attribute. First, second, third, delimited by these commas. So there's supposed to be question mark periods. And, it could be, maybe it'll work, maybe it won't. There's all kinds of weird scenarios that could pop up here. So it's just difficult to query composite attributes. And I'm just trying to give a simple example here. Okay. So how do we get rid of comma? How do we get a composite of attributes? Under most circumstances, composite attributes should not be present. Composite attributes can be replaced with multiple attributes well, there's two ways of dealing with it. We could replace the attribute with multiple attributes in the original entity. So instead of having a name in the company for the employee. Instead of having a table with, so just scroll this down and get rid of it. Employee, and we have a name, which is the composite. We could do F name, just split those into three additional, three individual attributes: first name, last name, varchar, 50 or whatever, and then middle initial, which is maybe a character 1. So we just basically, in the attribute, in the entity, in the table, we break down those individual components, first name, comma, last name, comma, middle initial, into their own attributes. And now we can write a very simple query, where, where last name equal, Smith. And there's no funny business with trying to parse out that name using the commas as delimiters and so on. The second is we substitute the composite attribute with a new entity. So we create a new weak entity, and then we associate that new entity with our table. So if we had, again, address was a composite attribute of, in our original table, in the employee table, we had an address column, which had that, 5 elements delimited by commas. So, well, we could do it a couple of different, we could do a second way, actually. We could, in fact, create an employee table and do what we did with first name. We could have, instead of an entire attribute, we could have a column for street address 1, street address 2, city. This is all on the employee table still. State and zip. Okay, so that works, but there's a restriction with this. What is that restriction? So somebody write me back here. What's that restriction? Serious restriction in the association between employee and address. So 13U is supposed to be online. Nobody has an idea? Of placing each component of the composite attribute for address into its own column in the employee table. All right. How many, well, then let me go a step further. How many addresses can we associate with a customer with the scheme? Yeah, just one, right, Jason. Just one. We can only have a customer. We can have an address. I'm sorry, we can have a customer and we can have address 1 to 1 because we can't fit more than one address in this, in one row. So that works. I mean, if the requirement allows that, if that's actually a superior solution. We'll talk about why in some ways. But if we have, a 1 to n, if we have one customer for many addresses, then all we have to do is we have to have an employee table with just the employee information, first name, last name, and so on. Then we need an ID. Let me put an ID here because that's something important. First name, last name, middle initial, and so on. This supposed to be an N for last name. And then we'll need an address table with street address 1, street address 2, city, state, and so on. And one very important component is we need the customer ID, which is a foreign key, back to the ID attribute, the primary key of the employee table. And so that makes this a weak entity, and this makes this a strong entity. Okay. Okay, so that's how we did that. We extracted that weak entity, the composite attribute from the employee table, and we split it into its own table and made it a foreign key back to the old name. And now we can do many. We can have many addresses. We can have many rows in the address table for the same customer. We can have address 123 Main Street for customer 1, and 345 Southern Street, also for customer 1. 2 rows, 2 addresses, 2 instances of address, but both, oops, sorry, that's, oh man, I can't believe I did that. Also associated with customer 1. All right. All right, so there we go. What's the advantage? I'm kind of getting ahead of myself, but I said it already. What's the advantage of this? Does anyone have any idea? Why would we like this? What would be the advantage of putting street address, those 5 elements of street address, into the employee table, combining essentially both employee and address information into a single entity? We can only model one-to-one, but what's the advantage? Think in terms of performance. Yeah, less time to retrieval. If this is an example, if we want to retrieve a customer and their address, we'll have to do a join. We're going to have to join, the customer table with the address table, and that's going to be expensive. We're going to access 2 tables to match on that customer ID. Whereas in this example, we just do a simple select on the employee's ID, and we'll get back the employee data and their 1 address. So the performance here is really much better. And in fact, I kind of lied before. We can actually represent multiple addresses for a customer. It's just that we would need a different technique. We would have to duplicate the customer 1 address information with their address 1. And then if we wanted multiple rows for customer 1, multiple addresses for customer 1, then in the same table, we'd have a second row with customer 1 row's data duplicated, but address 2 data. So we would represent 2 addresses for customer 1. We'd have 1 table that combines the customer with the address information. The address information would be unique for row I and row J, but the customer information would be the same. And but that would give us the facility we're looking for. Would give us performance, because we can now retrieve these 2 customers from a single select, but still get maintain 2 addresses for that single customer. And so I'm not going to go any deeper into that, but that is a very valid technique in order to optimize, the retrieval of a customer and its and their address information. I was thinking of adding credit card here, but that would definitely complicate things more than I want to. All right. Multi-valued. So that's it for a composite. Let's talk about multi-valued. A multi-valued attribute describes in a single attribute a single thing, but with multiple distinct choices or values. So as an example, we have a customer, back to ecom, and let's say we want to represent the customers, or we want to capture, persist, the customer's favorite colors. For maybe this is a ecom site that is centered around paint or fashion or I don't know what. And anyway, we want to allow the customer to store or to specify and then store their 1, 2, 3, 4, 20 favorite colors. Well, that's a multi-valued attribute. The same, we're capturing favorite colors, but we have multiple choices of that favorite color. So one way of doing it is kind of what we saw before. We could have one attribute of a string type, and we could have each value, each color, and then separated by a comma. So there's 3 color choices stored in a single attribute. That's a multi-valued attribute. And just like and this would work, but it would again make querying difficult. I don't want to go back into that whole thing, but if we wanted to identify a customer whose favorite colors are blue, then we might have difficulty distinguishing blue from navy blue. I don't really have, I should put that in this as a choice, blue and then navy blue. Green, and then that way I can refer to it back. I don't know why I don't think I was. Okay. So navy is a valid color, but it's different from blue blue. If you ever looked at online, there's a term for this, but they're 2 distinct RGB values, that's for sure. And oh, that's not a good idea. One second. I'm fiddling when I shouldn't be. Okay, so we can't distinguish. If we say search for a string with blue in it, and we don't know where it could be. Navy blue could be the first or the second or the third. Blue could be before blue. Navy blue could be before blue or after blue. So we can't really even use the commas like we could with the composite attribute, where we knew that the first section had the street address, and the second section, delimited by a comma, had the second street address, and the third section had the city. And we could write a query based on commas to target particular sections in our select. We can't do that here because there's no ordering. Navy blue could be before blue, or could be navy blue red, or in this case blue navy blue. So all we can do is like. If we just say, if we use like, I don't really have it here, but if we say like blue, if we just basically want to select customers whose favorite color is navy blue, and we say like blue, then we're also going to hit blue. We're going to hit the customers whose favorite color is only blue, not the special navy blue. Now, I know that sounds, a little bit, detailed, but this kind of, this is supposed to be a simple example of a more complex problem. And so just take my word. So how you fix that? Well, just like before, we can take and, let me see here. I took that out. Okay. So we can look at a slide here, and leave it. We could. I think I'm going to see this again in a later slide, but anyway, we started out with a fave color, and we could have broken that into 3 columns. Fave 1, fave 2, fave 3. On the customer table. And so we get a red here, blue here, and navy blue here. But that's going to make querying difficult as well. And I don't want to go into all the details here. So the solution is to take, again, just like to build a weak entity. We have a customer table with an ID and all the additional information. And then we create a second table, and we have 2 rows, just 2 columns in this. We have, for the first or last, doesn't matter, customer ID, which is a foreign key back to primary key, and we have a color, blue, for customer 1. Later on, customer 1, navy blue, and so on. So any number of colors any number of rows can be associated with a given customer, and the downside again is Now, when we want to retrieve a customer and their favorite colors, we have to do a join between these two tables, and that's that has efficiency. That has more additional processing. All right. So composite and multi-value attributes cannot be effectively queried. How do you identify customers living in a particular city? Kind of did this already. How do we identify customers whose favorite color is blue from navy blue? Kind of did that already. They can't be indexed or grouped. If I want to index by zip code for whatever reason, or state, doesn't really matter. If I'm going to be searching by state or zip code, I can't index just the zip code component of a composite attribute. So if I want to do a search for customers within a single index, the database will have to do a table scan comparing each composite address to our wildcard that we showed earlier, and that's going to be very slow. So we can't index on individual components of composite attribute, which is going to make querying very slow. And we can't represent multiple indexes, whether, with a single attribute, composite attribute. We can't represent multiple addresses for a given customer. That's a problem. But as I said, composite and multi-valued attributes have better performance because we're not retrieving the data and that information with a join. Right? So we can do it without a join. And as I said, weak entities require n+1 IO operations because we're going to have to retrieve data from the customer table and from the color table in this case, or from the customer and the address table. And the database is just going to have to look through more tables, performing more IO operations, which is going to hurt performance. All right, stored versus derived attributes. So a stored attribute is is physically stored in the database. And a derived attribute is an attribute that is derived usually by the select. So any query that performs an aggregation, so like if we want to go back and look at the examples for minimum, average, and max. We wanted to identify the average salary of employees in a particular department. Well, our system is not storing the average salary individually or by department. Instead, we have to write a query that will use the aggregate function, AVG on salary, and this value will be derived at runtime when the query is executed. So stored attributes are just basically information stored in the table, the first name, last name, date of birth. That's a stored attribute. A derived attribute is an attribute, or salary, individual employee salary is a stored attribute. But if we want to know the average or min salary across a set of customers, employees, then that's going to be a derived attribute because the database server is going to generate that value when the query is executed. Okay, so that's a two difference there. All right, what are we on time? Well, we still have 45 minutes. So let's take a whack at this. There's actually a lot here. We're not going to finish it. I want to finish this today. I'm always tempted just to remove this. So what I have at this section, the remainder of these slides, the remainder of this section, is a discussion, drink of water there, a discussion or information from my software engineering course. So I've taught software engineering for a long time now here at UTD, and so I have a full section on the analysis phase. And I think that this information is really useful for database because as as pointed out earlier, the entities during the analysis phase of the software development lifecycle, one of the goals is to identify the entity classes and service classes. So this is before, independent of the software design that will manipulate, CRUD these entities. So this is, again, especially important if we are unfamiliar, as the development team is unfamiliar with the problem domain, then we want to spend a lot of time um, analyzing the requirements, analyzing the problem domain, and identifying the entities and their attributes before we start to write the software, data structures, and so on in the next phase. But as we said already, those entity classes we identify are often persistent. In fact, I'd say most of the time they're persistent. And so, if we want to persist an entity class, well, we need a table. And so obviously the identification of the entity classes from software development, feeds right into the identification of the tables that we need in our schema for our database design. And so I have in this section some slides that go over, just a few points from my analysis section from my software engineering course. So let's just see how much of this we finish in the next 45 minutes, and just leave it off. You can look it over if you wish. So the analysis activities, again, this is very software oriented. It builds a bridge between requirements and design. So during the requirements phase, the development team is responsible, or takes on responsibility of gathering a set of requirements, formal requirements, and non-functional requirements, functional and non-functional requirements that describe what the system needs to do. And then the design phase, the team is supposed to be designing the algorithms, data structures, particular technologies that will be applied to implementing the services needed to build a system. And so between the two, between basically just writing out what needs to be done and deciding how we're going to do it, we have a set of activities that are designed to basically elicit a better understanding of the problem domain, so that when the team enters the design phase and they're focused on algorithms and technologies and so on, they're very unlikely to recognize gaps in their understanding from the requirements. It's just human nature. Only really do one thing well at a time. So by spending a little bit of time, maybe a couple of weeks, depending on the project schedule, on analyzing and recording essentially entities and services from the requirements, then those will feed into the design, the software design. But again, we stand a much better job of having captured all of those details that were hidden. Again, we could have hundreds or thousands of requirements, and so it's very difficult to design the software against simply the requirements and be assured that every one of the requirements is being met by the software design. Much better chance of the design meeting the requirements if we spend a little time just analyzing the problem domain and ensuring that that this analysis captures all of the features of the requirements. Anyway, take my word on it. So goal of the analysis phase are to build representations of entities in the problem domain, to understand how those entities contribute to providing the system features as defined by the requirements, establish a basis for the software and database design. So developers build analysis models. Now these are UML diagrams that identify the entity classes, their properties, maybe I could say attributes here, properties from software engineering, attributes, properties, same thing, and the associations or relationships between them. And we usually express these in UML class diagrams. Now you can also, during analysis, if you wish, start your software design, your database design, and do some ER modeling. But I would wait to finish the class diagrams before I started trying to build the ER diagrams, because if you try and build class diagrams and ER diagrams simultaneously, then you have to make sure that any changes to one are reflected in the other, and there's just no point in that. And then translate use cases into interactions between classes. So as we said before, not only are we interested in capturing the entities, the things in the problem domains, and their properties or their attributes, but we also want to identify things, operations that the system needs to accomplish or implement according to the requirements. And we want to be sure that each of those operations um, is possible, has the system maintains the information needed to implement those operations. So as an example, I said already, the idea is there's a requirement for that um, customer purchase report by date range, and does the system classes maintain the information needed, the associations needed to associate a given customer with the purchases they've made over a given date range and so on? And is that information then captured in the class diagrams, and then has that information been transferred to the ER diagrams, when we go to build the database? So we just basically have to identify all of the operations on the data and ensure that both the software design and later the database design can meet those operations, those services requirements. Okay, here's an example of a UML diagram, and I've added the IDs here. And also another thing to notice is this is a weak entity, but I put an ID on it as well. I kind of wish I didn't because it make the point, but I did anyway, and I don't feel like I'm not taking it out at this moment. Also, this games I owned, they're kind of like weak entities too, and don't really need this. Maybe I'll think of taking them out later. We don't really need an ID for games owned or games played either. These are join tables between the player. So the player owns a particular game. So each row in this table, or each instance of this entity, has a particular player and game ID, which signifies that player 123 owns this game, and so on and so forth. And also including the date they purchased and how much they paid for it. Just same thing of games played. We're basically associating a player with a game, and then what their the time finish and their high score or the score they earned or something like that. So, but this is a class diagram. This would translate into Java classes. And okay, and so the analysis model produces 3 database schema artifacts. So from the point of view of translating our analysis model into a database schema, we can think of 3 artifacts. The entity classes identified by the analysis that require persistence. So we said before, customer requires persistence. Shopping cart may not. It really kind of depends on the application's requirements. Do we wish to retain the shopping cart from one session to the user session to the next? If so, yeah, we have to persist the shopping cart. If not, if we can drop the shopping cart after the user leaves and comes back to a clean, fresh shopping cart, no, we don't have to persist it. It's up to the requirements. We also identify the associations between them. Excuse me. And also their attributes, not really shown here, but the class and their attributes. And then the associations, whether it's a one-to-one or one-to-many. Here we had a one-to-many, I'm sorry, a one-to, well, 0 or many. And here we had a 1-to-1 or more, saying that each player must have at least 1 credit card. But a player maybe initially anyway, a player has never hasn't purchased any games. So if they haven't purchased any games, they're certainly not playing any games. And so that's why we allow no game zone to be associated with the player, because there may be players that sign up, provide a credit card, but never actually get around to purchasing a game. And also, again, we're going to identify all of the reports and other operations that are going to be executed and ensure that the database schema provides those data, those attributes, the tables, attributes, or associations between tables needed to, produce the report or whatever service, implement whatever service, the requirements are calling for. Analysis modeling focuses on the what, meaning the how is put off till later. So what we're going to focus is on what and to defer how until we enter the design phase. What, meaning what objects does the system maintain and manipulate, CRUD? What are the properties of those objects and what associations do those objects share? So we're just basically going to identify the things, what questions, and then how do we implement this feature? We're putting off into the design phase. How does these models translate into software classes and database tables or technologies, particular to other technologies? We don't want to think about that now. We want to focus on just understanding the problem domain and leaving how we're building services to the design phase after we're comfortable that we fully understand the problem domain. Responsibly driven design. So there's an interesting, I should put this on this, I don't have to put this on to the supplemental material section. There is an excellent paper and books on how to perform the analysis phase of a software development project, and it's kind of embedded into a process called responsibility-driven analysis and design. And this goes way back, way back to the late 80s. It's how I learned object-oriented programming, so I guess I might be a bit biased. But in responsibility-driven design, the idea is to focus place ourselves in a mindset that has us asking what are the responsibilities of the system. So that's kind of like our requirements. What is the system meant to accomplish? And then who, in terms of classes, who is responsible for implementing those responsibilities? There's two responsibilities there in that sentence there. But what class takes on those responsibilities? What class in the problem domain have we identified that seems like a good match for that responsibility? So if the responsibility is to maintain the customer's information, well, that's a good match for our customer class, entity class. If the requirement is to look up a customer's purchases by a date range, as I said before, well, that sounds like a responsibility that might be accomplished, might belong to, I should say, some sort of report generation class, or some sort of customer report management class, or something along that line, some service class. But the idea, again, is, first of all, we identify the responsibilities that the system's requirements imply, and then for each of those responsibilities, we examine the current set of classes in our design, and we pick that class which seems to be a good match. It seems to be a natural match for that responsibility. And the result would be a set of classes which are cohesive. And where I could talk about cohesion here, I don't think, but cohesion, of course, is a driving principle behind software engineering, good software engineering design. Again, I'm going to put these papers out on the supplemental material. I forgot to do it, but and you should look that over. Anyway, so, well, I already said it. Identify responsibilities the system has to fulfill, and then for each responsibility, kind of like a requirement, we assign that responsibility to a class. So either a class that exists within the problem domain, or maybe a class which has not yet been added. So if and I'll just kind of, if we've identified a responsibility, we're early in the process, and we, have identified responsibilities for maintaining the customer's address information, we might ask ourselves, well, maybe, okay, we're thinking to ourselves here, that address, that belongs to a customer, maybe we add that to the customer class, like the composite attributes we talked about earlier. And, maybe that doesn't smell right, it doesn't feel right. We say, there's going to have, we're going to create a class that lacks cohesion. Because if we combine the customer's address with the customer personal information, we'll have a single class which is maintaining two sets of information, customer information and address information, and that kind of stinks. And it certainly lacks cohesion, so let's create a new class. This is our thinking, let's create a new class. Let's create we're going to create an address class added to our design, And that new address class will assume the responsibilities for maintaining that address information. Now that sounds pretty obvious, but that, more subtle. A real system has much more subtlety to it, and and it's up to the skill of the developers to identify responsibilities and then to identify the class which is the best fit for that responsibility. But the point is, I guess I didn't say this before, let me say it now. The main point in my thinking is this is a much more natural, more intuitive way of performing requirements analysis. Instead of sitting there and trying to go with the subject matter expert and identifying these statements. The system shall do this and the system shall do that. And it's more natural. People, react more naturally. They do a better job in terms of thinking of, well, what are the responsibilities? What should the system accomplish? What are, and then stating them as responsibilities, thinking of them as responsibilities, and then considering the role that each class plays in our design and identifying the class which seems the best match for that role to take on that responsibility. And if none of our classes seems to be a very good match, then create a new class and chuck them into that. But again, it works out very well. It's been, again, it's one of the first, at least in my mind, it's the first way I learned to build systems. So I'm going to skip this. I'm going to skip this. But if you're serious about software engineering, you should be familiar with these three ideas: entity, boundary, and controller classes. And again, I don't want to go into that here. In fact, I'm looking at the time and kind of running out. So, but this comes from the unified process. And so this is very similar to model view controller, MVC. You may have a lot of times people have seen the MVC pattern, but they haven't seen the entity boundary controller pattern. So you should be familiar with this. And again, if you're familiar with the unified process, then this is a very important concept, a mechanism for categorizing classes in our software design. I guess I'll mention it briefly because it's going to be right here. Entity classes, boundary classes, and controller classes. An entity class represents a domain-specific object in a problem domain. So that's what we've been talking about: customers, purchases, products, so on. Those are all entity classes. And so that's good. And usually we persist the entity classes. Boundary classes represent the boundary between the system and users or external systems. So all of the service endpoints, again, this may be a little more complicated than some of you used to, but what does that mean? The interfaces. So one of the most obvious forms of an interface is the user interface. Interfaces just don't spawn out of nothing. We have to design, implement as classes, user interfaces, and then those interfaces might be deployed in a phone application or a browser app or whatever, however. And so we need to identify them. And so interfaces is a user interface is a very obvious type of boundary class, but also, and I don't get too deep into it here, but if we're developing a web service, then we have a set of service interfaces that clients will connect to and access over the network, and those service interfaces become our boundary classes. So it just really depends. Some systems don't support a user interface. They provide a web service interface that external clients connect to, and that's how they make their money. But both of those are examples. Services and user interfaces are examples of boundary classes. Controller classes then are the most complicated. Controller classes implement workflows. So if you have a workflow for register customer, if the customer decides to register with the website, well, then there's going to be a workflow of gather information from the customer, verify that the information they entered through the screen is correct or valid, build an instance of the customer object from that information provided by the user in the screen, and then access the system's customer DAO and persist that customer's information, or maybe check to see if that customer has already been entered into the system somehow. And if not, then enter it into the system. So my point is there's a workflow, a series of steps that are to be implemented to perform the input, validation, persisting of a new customer. And every workflow, every major responsibility of the system, whether it's add new customer, add products, checkout, select product, product search, all of these are responsibilities of the system, and each needs its own implementation, its own workflow, and so each of those would have its own controller class in the design. And so I can't emphasize this enough. You really should look into this because this is a very natural way to build web services, to build services in general, is identify the controllers for each of the major features to be implemented, services to be implemented, and then identify which entity classes are being CRUDed and manipulated by those services, and then identify any interfaces that are needed to allow that, provide that, to provide users or external clients access to those services. Anyway, controller classes. Let's see here. Where am I in time? A little more time left. Entity class modeling. So focusing on entity classes. Major activity in the analysis phase is identifying the system's entity classes, and these are identified from requirements, from the SME, from use cases, not really mentioned in this slide, but use cases or stories. It depends on the process. Analysis modeling focuses on the problem domain features, identifying classes and concepts that are important to the design and its implementation. The analysis model should be relevant to the system solution, to the customer's problems. So if an entity is not relevant or contributes to the problem solution, we don't include it in the model. So if we may think we see an entity in the problem domain, and it might be there, but if that entity doesn't contribute to the system solution, if it's not part of the solution that we're building, then we don't want to include it. So even though it may be a valid feature of the problem domain, I can't think of anything off the top of my head, but if it's not valid part of the solution, then we don't add it. I can't come up with any ideas. Anyway, okay. Oh, and also we're not including implementation. We're not doing design. So we're not interested, during analysis, we're not interested in how these entities and services, controller classes, are going to be implemented. Just basically create classes which are placeholders, especially the controller classes. And then once we're comfortable that we've identified all of the entity boundary and controller classes needed to implement the requirements, then we transition, software development team transitions from analysis into design, where we then fill in, flesh in the details, especially in the controllers. How does this workflow going to be implemented? What tools and libraries will we need to implement it, and so on. But again, we want to split the two apart because developers tend to start looking at implementation details, and they're going to drill right down on those, even though the analysis is half over. And so it's really, if this is a team effort, and it should be, somebody needs to keep the team on track. We're doing analysis. That's a very interesting question, but we're focused on analysis at this point, and let's defer that question to the design phase or something like that. Anyway, analysis, entity classes, and entity classes, things found in the problem domain. We've mentioned this already. Generally speaking, nouns found in the requirements. So you've probably seen this already, but this should be nothing new. If you maybe covered this in software engineering, not software engineering, but in the second programming, where they get an object-oriented. You gather requirements. The most simple thing to do is you gather requirements from the customer. You have these statements. The system shall do this, and the system shall do that. And then in that, we have nouns. The system shall maintain customer. Well, customer, that's a noun. So that's something that we're going to have to, it's a thing in the problem domain, something we're going to have to build and maintain and persist. So if we simply just start out as developers, looking at the requirements and picking out all the nouns and listing them separately, And if you're ever interested, you could use something like CRC cards. You want to look that up, CRC cards. I think class responsibility collaboration cards. Then that's one way of recording, picking out and recording the nouns. And then we can, so that's a good way of starting entity classes. Just look for the nouns. And then think about things that are being produced or manipulated. What are the things that the system is producing, is designed to produce, or what things does the system manipulate? CRUD. So, question, is the purchase, and is it, okay, we have this concept in the econ of purchase, okay? Is it a noun? Well, it's both a noun and a verb. So it's a verb in the sense that we can say in a requirement, the customer purchases products. So the purchase is an action taken by the customer on a product. Okay, so it sounds like a service. We need a purchase service, a purchasing service or something, because it's an action. But it may be an entity. What makes it an entity? Well, maybe we need to store information about each purchase. You know, we want to capture, when the purchase was made, how much was purchased, and other information about that purchase. And so all of a sudden, purchase, although it is an action taken by a customer, um, it also now has become an entity because for each time a customer makes a purchase, we want to record that information. And so we need a class, we need an entity, and why not call it a purchase? So we have a purchase class all of a sudden. So, you need to think about all aspects. A purchase is both an action and it's an entity that we need to capture specific information about each individual purchase made by a customer. And so now we suddenly have to persist that information as well. And all of a sudden we've gone from not having a purchase table to having a purchase table. Entity class differentiated by these three things. We have a symbol, intension, and extension. So we're thinking of something in our problem domain, and when can we say, is this thing an entity? Well, we could say, ask ourselves these questions. Does it have a name? Well, usually it does, or how would we know it? But maybe it's a concept. We haven't given it a name yet. So if this thing that we're considering to be an entity has a name, a symbol, then okay, that's good. That's step one. It has intention. Does it represent something in the problem domain, a thing in the problem domain? So it could be a physical thing, a customer, or it could be an abstract thing, a purchase. But it's still something in the problem domain. And so we want to, that bugs me, we want to give it a name. And it has extension. Are there unique instances that differentiate one purchase from another, that differentiate one customer from another? Well, customers are easy because customers represent people registering with our system. Purchase, if you think about it correctly, that's pretty easy too. This purchase made today is distinct from a purchase made tomorrow, and so on. Or purchase, maybe I make two purchases on the same day, so at time A and time B. So they have unique instances of a purchase. So yeah, so that would make customer and or purchase an entity based on that criteria. If we can't identify a customer's extension, we may have a verb. So another example is update. We may say to ourselves, and this is a little more subtle, the requirement is that a customer is able to update their information. So maybe the customer initially enters in the wrong birth date. So we have to provide a user interface that allows the customer to review their current information and then give them the option to update some of that information. Maybe birth date can be updated, but I don't know what else. Pretty much anything, I guess, could be updated, except for maybe the email address. So if we're using email addresses to uniquely identify each customer, if we change the email address, I guess that would be allowed to. I can't think of anything we can't allow. But at any rate, is that a is that an entity? Is update an entity? Well, it has a name, yeah. It's something we find in the problem domain, customer update, but does it have extension? Do we want to, you know, differentiate, if you will, one instance of an update from another instance of an update? And that really depends on the requirements. Um, I'd say for the most part, no, that update is strictly a verb and it's an action for a service that a customer will invoke and update their information, their identity information. But on the other hand, think of security. Maybe this information is sensitive and we want to record each time a customer's information is updated. So, and maybe we'll want to include the ID of the authenticated identity of the user that makes the update. And we want to record the time that the update occurred at. And maybe we want to record the IP address that the update request came from. And what else? Maybe we want to record the original value of the birth date and then the value that it was changed to. So we can keep some sort of auditing trail. And of course, birth date is kind of a simple thing, but if we're updating a account from a bank account, for a banking system, then all of that information certainly suddenly becomes much more important. You know, what was the ID of the client that requested the transfer, the bank account update? What address were they coming in from? What was the previous balance and what was the new balance, and so on. So, depending on the requirements of the application, update can remain a simple operation where we're not recording individual updates information, or it becomes an entity class in our design if we need to capture information about each instance or each occurrence of an update operation. So it depends on the requirements. Guidelines for my time. Okay, a few more minutes left. I'm not going to quite finish. Identify noun phrases and use cases, brainstorm with a category list, reuse entities from schemas found in previous systems design. So again, if this is the third or fourth ecom system the user or the group has built, well then, I would go back and look at those old database schemas of those old class diagrams and start from there, because chances are a lot of not the majority of information for implementation A, will be relevant to implementation B, new implementation. Uh, Identify noun phrases. Noun phrases are statements. Noun phrases are statements that operate on a noun. So, for example, we could say purchase, but there's all kinds of, or payment. I'm sorry, here we're supposed to be payment. So, but there's all kinds of different payments. There is a purchase payment, a payment made by the purchase. And then there's payment history, a list of payments that have been made over time. And then maybe we're also maintaining the concept of refunded payment. So we have a purchase payment, and then the person returns that product. They want to return it. And so we're going to make a payment back to the customer's account of some amount. So that's the idea of a noun phrase. Each of these is a noun phrase, but each is significantly different in the role they play in the systems design. Of course, you want to analyze requirements, use cases, and other project documents, obviously. Collecting detailed requirements will reduce better coverage, a more complete. So although gather requirements is a pain, and that's one reason it's detailed, it's a lot of detail. It's just very unsatisfying to do for some people anyway. Hiring somebody to do it for you as a developer, it's nice to have that business analyst that is basically going to do it, has been trained and knows how to interview the individuals and get the information and so on. Look out for duplicates. Purchases and transactions are the same thing. Perhaps we've identified a purchase in the problem domain, and we have also identified a transaction in the problem domain, but it's possible that they're the same thing. That transaction is actually a purchase, but a different name, and we'll just combine the two together and eliminate transaction, keep purchase, and we'll have cleaned up our design. Category lists. So what we do is, this is a brainstorming technique, and it's from that responsibility-driven design. We can identify, just basically go through each of this list. This is a brainstorming activity for the entire group. So this is not something you would do individually and then come back. This would be a nice thing to do in a room as a group. Remember the days when we used to get together in rooms, and then go through this and other list and think to ourselves, okay, well, what physical tangible items are in the requirements? What kinds of specifications or descriptions, places and locations, transactions? Just go through and brainstorm as a group and identify um, nouns or entities in the problem domain that fit into one of these categories. And it's possible, not every one of them applies to the problem domain, that the application you're working on, but it's possible, you'll think of one or two roles or sources of information that, you hadn't thought of earlier, that maybe weren't captured in the requirements, but certainly need to be in place to make the system work. So this is, again, a category list, or as a brainstorming technique, and it's well documented. You can look it up if you're interested. We're also interested in associations. Almost out of time, I realize. Not only are we interested in the individual entities, but the associations they maintain. And so those are captured in UML by 1 to 0 or many, 1 to 1 or many, and 1 to 1 without any notation. And of course, those play a role in defining the foreign key associations later in the schema design. Skip. Many-to-many associations have to be implemented, are important to capture. So if you have an N-to-M, we don't have one here, but if you had an N-to-M association from this entity class to that entity class, then when we develop the schema, we would have to introduce a join table between the two to implement that many-to-many association. So, in our UML, and I wish I did that here, I didn't. In fact, anyway, we have a many-to-many association from student section. One student can take many sections, and a section is attended by many students. And so in order to implement that in the schema, we have to need a join table that joins two together, and that's essentially what we see here. Quality of join tables. A join table is between at least two entities, but we can have a three-way. We can have two-way, a three-way joins. But be careful if you're trying to consider the fact that a three-way join or a four-way join is going to start to get very expensive in terms of processing, and it's a little bit hard to get your head around at times. And of course, we need foreign keys. We talked about this. So here's an example of a three-way join where we have works on. So in this example, this is the last almost, well, yeah, we're done. But here's an interesting example where, one of the shortcomings of the works on table, not shown here, was, if you recall, the works on table had three columns: the employee ID, the project ID, and then the hours. The hours the employee worked. But the problem with that schema is we're not capturing the individual contributions that the employee makes to a project on a day-by-day basis. Without, with the schema given in the example, we can only record the total number of hours that the employee has spent on that project. And we can, every time they log more hours, we increase the hours worked. But that is usually not sufficient, for some sort of time reporting application. We need more detail. We want to know that on a particular day, this employee worked this many hours on this project, and usually we also would include an area that the user, the employee, would fill in to say, well, on this given day, I implemented or performed this for the project, and on the next day, I'm performing some other thing. So give some explanation is required of what, for that 10 hours, what exactly was accomplished. And what, we'll say 5 hours on day one, what was accomplished, 6 hours on day two, what was accomplished. And so this schema implements that. We have the employee and the project just like before, but we added a third entity to the problem domain, works performed, and we gave it an ID, and it has the type of work. Maybe one is software development, two is business analysis, three is testing, and so on. So what type of work, the date and that the work was performed on, the number of hours that was contributed that day, and again, description. So with this three pieces of information, we can have an employee working on a project, and then each combination of employee and project can maintain multiple instances of work performed. Again, one's for every day that employee logs to a particular project. So that's a good example of fixing the problems with WorksOn, and by again extending the schema to represent with an entity that represents each individual contribution that an employee makes to a project. Okay, so that's it. Done. I actually finished most of it. There's a few things here, but we'll leave it alone. Um, all right, so thank you for your time. Thank you for attending, and we'll see you on Thursday. Any questions? If not, I'll let you go. All right, you're welcome. Take care. Stop recording. Yep, take care.